and welcome. I am Karen Fox, and we are here at Kennedy Space Center in Florida to talk about the next mission that NASA is launching, Solar Orbiter. This is an international collaboration between the European Space Agency and NASA, and it is going to provide the most comprehensive views of our star that we have ever been able to get. We have a panel of great speakers here today to talk to you about it. We have Daniel Mueller, who is the project scientist for Solar Orbiter at ESA. We have Nicky Fox, who is the director for Heliophysics at NASA headquarters. We have Guenther Hasinger, who is the director for science at ESA. And finally, Thomas Zurbuchen, who's the associate administrator for science at NASA headquarters as well. Solar Orbiter will have a launch window that opens on Sunday, February 9th at 11:03 p.m. East Coast time. And with that, we're going to get started talking about this mission. Daniel, you've been with the mission for 13 years?
That's right. It's been a long time. We're nearing completion. It's just a few more days to go, and we're excited. And
Tell us why. Why are you excited?
I think we have the best job in the world because we are going out there to explore the sun and the solar system. And Solar Orbiter will be the first time that we send a satellite out to take images of the sun's poles. And in addition, getting the first ever data of the polar magnetic field. And we believe that this really holds the keys to unraveling the mysteries of the sun's activity cycle. And in addition, we will also monitor the far side of the sun, which we cannot see from Earth, and combine that with data from satellites and ground-based telescopes to provide a full 3D view of our star. And Solar Orbiter is really a laboratory in orbit. We have a suite of 10 sophisticated instruments that will work together to track the evolution of eruptions on the sun from the surface out into space, all the way down to Earth.
Thank you very much. It's an exciting mission. We're going to go to Nicky Fox. Tell us a little bit about the context. How does this fit into why we want to study the sun?
Thank you, Karen. Yeah, it's a very, very exciting mission. Our entire solar system is really governed by the activity that comes from the sun. There's a continually streaming kind of soup of energetic particles that moves away from the sun, bathes all of the planets. We call that the solar wind. And not only does it do that, but it actually carves out our place in space. So as the solar system is going round on its journey around the Milky Way, we are protected from interstellar space and the vagaries of what is out there by the solar wind and the protective bubble it creates. Sometimes in this continually flowing soup, we see these very energetic kind of explosions on the sun. We call them coronal mass ejections, and we see them embedded in the solar wind. When they arrive here at Earth, they can really disrupt our technology. They can cause problems for GPS, for communications, and of course, for our astronauts. We worry and we want to protect our astronauts. The solar wind can even cause issues for them even while they're in our protective magnetic field. And so as NASA moves forward to return to the moon, to Mars and beyond with our Artemis program, missions like Solar Orbiter joining our fleet become really, really critical.
Thank you very much. Daniel, with that background, what is Solar Orbiter doing to contribute to that? How is it going to help?
Well, Solar Orbiter is special because it's really the first mission to try to link the sun to the heliosphere and establish a cause and effect, a relationship between what happens on the sun and what we observe in the near-Earth environment. And in particular, we want to find out in detail about how the solar magnetic field works. So we know that moving charges generate a magnetic field, which is in a way the opposite of what happens in a light generator on a bicycle. And we know that the sun exhibits this 11-year activity cycle. People have been observing the sun since man invented telescopes about 400 years ago, but we don't really know what drives this cycle of 11 years and the amplitude. We cannot predict how strong the next cycle will be. And we believe the sun's poles are really key to understand. And we know that the sun's magnetic field is transported a little like on a conveyor belt from the equatorial regions of the sun to the poles and presumably back. And that part we don't know yet. And the only way to find out is to really fly to an altitude above the sun where you can look down on the sun's poles. And that's what we'll do for the first time. And on Solar Orbiter, we have not only one instrument to measure magnetic fields, but actually 3. So we'll use both the sense of touch, a bit like Parker Solar Probe, that's almost touching the sun literally. We're measuring the plasma at the location of the spacecraft, and we'll have 2 of these sensors, and we'll also have a camera that will use the magnetic field information encoded in the light, and thereby we try to connect the magnetic field on the surface to the magnetic field we measure where the spacecraft flies. And ultimately, the magnetic field shapes everything, this entire plasma bubble, and it also contributes to the way the solar wind is accelerated. So we understand roughly how that works, but not really in detail. And combining Solar Orbiter and Parker Solar Probe will really provide us with powerful tools to do that.
Take us even a little further. You talked about some of the instruments on board. What are the other instruments that are really going to help us do this?
Right. So we have 10 instruments on board, so a really impressive suite. And as the missions project scientist, I love them all equally. They're all great. And they work even better as a team. And the unique thing is we have these 4 sense of touch instruments that measure the solar wind as it zips past the spacecraft. And we have 6 telescopes that observe the light from the sun in different parts of the rainbow spectrum. And 2 of those are so-called coronagraphs, where we block out the light of the sun itself to image the faint emission of the environment around the sun, the so-called corona. And in addition, we have these sensors that measure, for example, ions in space. Like elements on the sun are not only hydrogen and helium, but also sprinkling of heavier elements like iron, oxygen, neon. We measure those at the location of the spacecraft. We really weigh the particles, but we can also measure the light that they emit on the surface, and thereby we have a unique way of linking the 2.
Great. So as you've walked us through this spacecraft, it is, of course, built on a legacy of all sorts of other observatories that have been looking at the sun. Nicky, give us a little bit more of that. How does this fit into our studies in general?
So I love the term legacy because we really do design our missions based on what's come before. We've had this long partnership with ESA. We had Ulysses that launched. We've, of course, had SOHO. And so going back to the launch of SOHO 25 years ago, there have been 13 solar missions. And so Solar Orbiter will be the 14th dedicated solar mission since 1995. And so we build on this legacy of these missions that have gone before. They tell us the questions that we really, really, really want to answer. And so we design our missions. And for me, the most exciting thing is we are welcoming Solar Orbiter into this huge fleet. Each of our spacecraft is designed to go to exactly the right place to do the science that we want to address. And so we cover everything from the inner heliosphere all the way out to the very edge, now into interstellar space with, of course, with our Voyagers. And so we put all of this together, just like Daniel said, the 10 instruments work together better as a team. All of those assets that you see work better as a team. It's an exciting time. Parker Solar Probe up there. Her 5th perihelion, we will be joined by our sister, Solar Orbiter, and they will start taking data together. Of course, just last week, we saw those fabulous first light images from the Daniel K. Inouye Space Telescope. And if we run the video, you'll see these little grains there. They're about the size of Texas. If we can run that, each of those cells is about the size of Texas. So it is just, as I always say, Karen, it is a great time to be a heliophysicist.
Thank you, Nicky, for that perspective on how it fits in with NASA. I want to take it to the European Space Agency and get a little bit more about that. So we have Guenther Hasinger, who's the Director of Science for ESA. Tell us how this fits into what ESA is doing right now.
Yeah, so we are really very excited that Solar Orbiter will join the fleet of missions that ESA has in the solar system. And similar to NASA and many of these things we are doing together, we have actually quite a number of missions. We are standing on the shoulders of giants in a sense of our legacy. Ulysses, Nicky mentioned, was the first one that actually went over the poles of the sun, but at a very large distance and with the eyes closed, so we didn't really get the information that Solar Orbiter will get. And SOHO is working since 25 years and doing excellent monitoring of the sun. But we also have sent something recently to Bepi Colombo to Mercury. We have plasma instruments nearby, the cluster mission, for instance. NASA has also a cluster type mission, MMS. And so Solar Orbiter will sit in this family of missions that are studying the inner solar system. And together with Parker Solar Probe and the Daniel K. Inouye Telescope, I regard it as a kind of an orchestra. Every instrument plays a different tune, but together they play the symphony of the sun. And it is quite fitting that just recently Eugene Parker himself has been announced to win the prestigious Crawford Prize, which is something like the Nobel Prize for astronomy. And so that he who has discovered the solar wind is now also awarded this prize exactly at the time when we formed this collaboration is really wonderful.
Thank you so much, Guenther. We are going to go now to Thomas Zurbuchen, who's the Associate Administrator for Science at NASA headquarters. And Thomas, you and I were talking a little bit before. There's actually a reason with all these missions that you're paying attention to why Solar Orbiter is particularly special to you.
Well, with Daniel, many, many years ago, as a scientist, before I stopped doing science and helped other scientists mostly, I actually was part of this early stages of that mission. We designed the mission together already as an international team. And then what we did is we came up with new sensors. There's one sensor on it, for me, a little bit more important than all the others. So for you, it's all the same. Well, there's that one that I worked together as a lead of the sensor lead, the heavy ion sensor. You talked about this weighing iron and oxygen. It's that sensor that I designed together with that team, and it's up there now on the rocket.
That is exciting. That's really exciting. So now give us a little bit more about all of the missions in the portfolio for science. How does Solar Orbiter fit into what NASA is trying to do with science and research right now?
So the first thing that's really quite obvious, and you talked about this, both you, Nicky, and you, Guenther, is it's a great time for inner heliosphere science. It's that the near solar physics is really, there's a campaign happening right now that's historic. It's unprecedented. And what's really critical is to get the best science out of this right now. It's just really amazing. What's cool, though, is that the science questions that are being addressed are actually really important elsewhere, too. Look at astrophysics. We're asking all these questions about finding planets where life could exist. So if you're next to a star that has enormous eruptions like they do, we observe with our observatories elsewhere, and basically every once in a while we wipe clean or burn off, if you want, the atmospheres of these stars. That's not a good place for life, we think. So really understanding the origin of activity, which is precisely what Daniel talked about earlier, is something that's of interest in many other domains. By the way, looking at polar regions, the importance of that, you can learn, for example, by looking at Jupiter with Juno. So looking down at it, the polar regions are very different than we expected, and there's a lot of puzzles about the magnetic engine of that planet. So we think of this as just such a critical element, both for heliophysics, but for science overall.
And of course, we have coming up another international collaboration with ESA, James Webb Space Telescope. So tell us a little more about that as well.
Yeah, I was just at launch readiness review, and one of the highlights for me was to turn around and see the European launch team right there sitting in the launch readiness review. So we're learning about each other's cultures, each other's processes, because next year we want to launch the James Webb Telescope, and we're going to do that on the European side, and really in Kourou, and the telescope right now, it's all folded up. Where they're doing some of the last changes before we do the final tests, so we're getting excited there also. So many of our missions are international, and so many people just don't understand. The science community is an international community. It's the natural way of doing work is an international way. Science unites all of us around the world, and Solar Orbiter and James Webb are just an indication of that.
Great. Well, thank you all so much. We are going to have time now to take some questions from the room. We also may have some people who have phoned in taking questions, giving questions, and we also are taking social media questions at #AskNASA. Yes, Marcia.
Marcia Dunn, Associated Press. I'm interested in the polar views of the sun. I mean, I don't know if you can guess what you're going to see. To me, it would look like the rest of the sun. But what in particular will you be looking for? Maybe there will be huge differences in the pictures. If so, what? And will you have the kind of resolution as we saw in the photo from the Hawaiian telescope with the Texas-sized, boiling bubbles there on the sun? I'm just looking for a little sneak preview.
Right. Yes, I think I can take that one. I think, in general terms, the sun's poles are still part of the solar surface. So in general terms, they will look somewhat similar. I think the difference really lies in the magnetic field. So this boiling surface with the granulation that will most likely look similar. But we are looking for indications of this conveyor belt mechanism where field submerges, and where you see indications of the next solar cycle popping up. So after 11 years, the sun flips its global field, like the Earth has done a few times in its history, but the sun does it on an 11-year scale. And we believe we will see indications of the next cycle early on in the polar regions. And these are small, strong concentrations of magnetic field that we'll see. And coming to your second question, I wish we would see pictures as we see them now from the Inouye Solar Telescope with Solar Orbiter. The Inouye Solar Telescope has a 4-meter mirror. I wish I could get the funding to fly that in space. So our instruments are slightly smaller, so they fit on the spacecraft. But we are going closer in, so we are going, let's say, inside Mercury's orbit, so we gain roughly a factor of 4 in terms of resolution. So we'll resolve spatial scales of the order of 200 kilometers, so you could see Texas for sure.
And could I just have the pros and cons of Parker versus Solar Orbiter? Could you sort of compare the two and talk about their strengths and weaknesses and how they work together to provide this total picture, please?
Yeah, they don't have any weaknesses. They only have strengths. And so, they are both going to exactly the right location to be able to do the science that they are designed to answer the science questions. And that is why it's so great that the two of them are flying together, and also with the DKIS telescope adding that high resolution. But for Solar Orbiter, the key thing, of course, is they're going out of the ecliptic, so they're lifting out of that plane where the planets all orbit to give us unprecedented views of the poles. And as Guenther said, we know the poles are exciting because we flew Ulysses over there, and we saw that with our in situ data, dramatic differences in the poles from solar minimum to solar maximum, but we couldn't see it. And we have models that have shown that there may be giant coronal holes that take up a huge area, and we just see the very, very edges of them from where we are. And so Solar Orbiter is designed to go and be able to really unlock these mysteries. Parker Solar Probe, of course, is going deep into the corona, orbiting right the way through kind of that action region, as close as about 3.9 million miles off the sun's surface. After her next Venus flyby, she'll be at about 8.4 million miles above the surface, so she's still got a long way to go. But the key there is that we're providing the in situ data. And so we've looked at the sun and all these other wavelengths. We've been in as far as Mercury. Now we're going all the way into the corona to actually touch that solar wind and be able to tell us exactly what processes are going on. We've seen great results already with the first couple of perihelion passes. We've had, the Nature papers, and then just last Monday we had 43 papers that were published in such a short time. So Parker already giving us great results, but it is just that partnership between Parker and between Solar Orbiter that we're so excited about. They're sort of just giving us there's very similar science questions, but totally different ways of answering those questions, and that's what makes it such a powerful partnership.
Can I add to that? Yeah.
Yes, please do.
So just to give you a little bit of a feeling how they are working, Solar Orbiter will go into a region where it is about as hot as a pizza oven. It's about 500 degrees hot or so Celsius. And you know that it has this very intricate heat shield that is keeping it basically safe from the sun. But then it has these little peepholes that open when we want to look at the sun, but then otherwise they are closed because the instruments are so sensitive, and the rest is basically shielded from all that heat. Parker Solar Probe is going even further. It goes into a place where it is actually millions of degrees hot, where it's flying basically through the corona, and there would be no way to open a peephole or something like that to look at it. So it cannot have a camera. And the two together are really perfect because, for instance, sometimes it is that Parker Solar Probe flies over the surface of the sun at a certain magnetic field region, and then Solar Orbiter is watching Parker observe and can actually connect what it sees to the magnetic field and can actually feed back the information. So it's really a perfect a dream marriage in heaven.
All right, we'll stick over to this side of the room, over here, the second row, yeah.
Hi, Mary Liz with Cosmic Perspective. So this is a really, really exciting time. And just to follow on this discussion, I'm always thinking about the Voyager spacecraft that have now kind of crossed that boundary line, right? Can you give us an update on how these spacecraft will work with the Voyagers to give us a really holistic view of the heliosphere? Maybe Nicky or whoever would like to answer.
Sure, that's a great question. And so, our fleet, we have these spacecraft that are in exactly the right place to do the job that we want them to do. And so, we now know because of Voyager and actually IBEX, which is imaging that region, we have a new mission coming online, launching in 2024 called IMAP, that is going to give us very unprecedented views of that boundary. And so now we are looking at the cause and the effect. And so, we know it affects the Earth. We have great sentinels here that are telling us about our space weather. But now with Solar Orbiter, Parker Solar Probe giving us all that information about our inner heliosphere, and now with the Voyagers, IBEX, and eventually IMAP, really focusing on that sort of tenuous boundary between our solar system and interstellar space. And we know that boundary cuts out about 70% of the cosmic rays that come from outside. So we know it's doing a great job of protecting us. But we also now know that entire heliosphere kind of breathes with a solar cycle. And so it actually shrinks and grows with a solar cycle. So, the sun is having a profound effect, or the solar wind, on everything. And so wherever we are, New Horizons is going to be giving us great data now past Pluto and into the Kuiper Belt. We'll be looking forward to more data from there. Also, we work with all our planetary colleagues, and so everything that Thomas mentioned, the poles of Jupiter, but we put everything together. We're heliophysicists. We're excited in data anywhere, and so wherever you go, we want your data. So yeah.
Do you mind if I add one connection that many people miss? So if you look at the whole space, in 3 dimensions, you basically said, where did that plasma, the solar wind, come from? At any one point, the majority of it over a solar cycle comes from the polar regions we've never imaged.
That's true.
And during solar minimum, which is where we are right now, 80% or so come from a polar region we've never imaged. We've flown through them with Ulysses, and we found that it's really different than the stuff in kind of where we hang out, with the Earth and the other spacecraft. Voyagers, or some of them, also kind of getting at that edge, but we're going to see it for the first time, that very source of space, of solar wind.
That's right.
Great, thank you. I believe we have Ken over here, and then we will come over to this side of the room.
Hi, Ken Kramer, Rocket STEM and Space Up Close. For probably anybody, I'd like to hear more about coordinated observations between Parker and between Solar Orbiter. And will this help you create a 3D picture of the magnetic field and the storms, and what will that gain us? Thanks.
Yeah, that's an excellent question. And really, collaboration has been at the heart of these 2 missions since the beginning. And as of a few days from now, we actually have a real trajectory that we can then connect. And we've already pre-planned for the last years. Also because Solar Orbiter is not a mission like SOHO, where you can replan on a daily basis and you can just drive it with a joystick. But we really need to plan months in advance, because we'll be so far away from home that we need to be careful to use our onboard data storage in the proper way to downlink the data while we still have space to add new data. And so we'll really have let's say, a long-term timeline that we'll populate together with Parker Solar Probe and make plans and see what science is best done at what times. And we'll try to be as flexible as possible to react to changes on the sun. But overall, really, collaboration is at the heart of driving this mission successfully.
And
Yeah, sorry.
I'll just add that, so from NASA's Heliophysics division, we actually have a coordinated program. It's a research program that we've put out to the community to really focus on linking the missions. It's sort of in three parts. One is really linking all of the inner heliosphere. One is looking at the inner heliosphere and Earth, and then one is looking all the way out. And so it really is to make sure that we capitalize we also including our ground-based colleagues to make sure that every single asset that we have can be used to really answer these questions in a very coordinated fashion. So, as Daniel said, we've worked together. In my previous life, I worked really closely with Daniel on the coordination of the missions. But now we're really broadening it into every possible asset.
Maybe just to illuminate the tricky background of some of these preparations, because Solar Orbiter is on a relatively large elliptical orbit. It is going close to the sun, but then it comes back to the Earth. So when it's close to the Earth, we can actually download a lot of data, but then we don't have the sun close by. When we are closer to the sun, then it's a factor of 10 less data, so we have to store them in between. And then Parker Probe has its own orbit, and so you have to look at the two orbits and you have to match them up so that they are kind of aligned at the position that you want them. That doesn't happen a lot, so you can imagine that these precious moments when Parker and Solar are actually right in the same direction are really looked at very favorably.
But I'll say it does happen more often than you might think. We got very excited when we started looking at all the different. There's the radial,
Yes.
then there's let's go around the Parker spiral, and then there's let's be in quadrature.
Yes.
There's loads of great science that we can do.
And then the quadrature is precisely related to the question that he asked.
Yeah.
The goal is to get three-dimensional structures that are coming out, and we'll get it for the first time because we can actually look at it from that and from the inside, right? With Parker being low and actually looking out sideways, and then Solar Orbiter this way, using the Earth as a third vantage point. It has not occurred that we had that kind of data. And yes, the three-dimensional structure is the goal.
Yes.
Fantastic. Let's come on over here. Yes, sir.
Hi, Jim Siegel with Spaceflight Insider. I wanted to follow up on a comment that I think, Guenther, you made about the peepholes. I believe, if I heard correctly in the prior pre-launch briefing, that those windows are once the spacecraft approaches the sun, those windows are open for 10 days and then they close. So I wondered, is that accurate? Is my understanding accurate? And behind that window, is it something like a camera where there's a shutter and it takes a quick look at something or measures something, and then are different instruments linked to the same window, or what? How does that work?
So there are 6 remote sensing instruments, 6 cameras, spectrometer, X-ray imager, polarimeter, and then also the instrument that measures the sound of the sun, the solar vibrations. And they are behind these peepholes. And the peepholes are only opened when those instruments are observing. And I think this is a 10-day period, right?
Right. I mean, being scientists, we always want to push things beyond the limits. So for all engineers in the room, yes, it will be 10 days. For everyone else, let's see. Maybe we can extend it, because everything is double fail-safe. These doors, the sliding doors, are the primary safeguard in case anything should fail internally to the instruments. Let's say if an entrance window to one of these cameras breaks, then we still have the window to keep the whole spacecraft safe. But even when the doors are open, we have developed new technologies, new coatings for heat-rejecting entrance windows that keep most of the heat away and only transmit a small part of the spectrum that we are measuring. And so the 10-day windows are centered around the most interesting parts of the orbit: closest approach, highest latitude of the polar observations. But we hope ideally to also take some observations in between, also to help other observatories like Parker Solar Probe get the full 3D view. And in addition, maybe that's one thing worth mentioning, is we have this wide field coronagraph that looks sideways over the edge of our heat shield. So it's imaging the entire space sideways to the sun. And that is very similar to an instrument on Parker Solar Probe, in fact, built by the same team. So that is, in a way, our fisheye lens to get the big picture.
Okay, so these doors that are behind the windows, they act as kind of a shutter similar to what a camera does, and or
No, the doors are the outermost part. They are on the heat shield. So they are protecting, I think we had a video of that as well, they are protecting everything on the outside. But even when they... That's right. It's like the lens cap. So these are the lens cap, and they are sliding because there's no one with an arm there to take them off. So they're sliding doors, and they're behind that. We have different mechanisms depending on the telescope. For example, the X-ray telescope only measures X-ray, so it has a beryllium entrance window. So beryllium is a metal. It's you can't see through it in visible light, but the X-rays just penetrate. So that is its way of protecting itself. And another instrument just lets more or less all the light in, and most of it goes straight out again through the side of the spacecraft. So that is the way of dealing with the heat. While the other one has a special coating that reflects all the thermal radiation and only lets a small piece of the rainbow through.
Thank you.
Mm-hmm.
Great, then let's take it back over to this side of the room.
Stephen Young with Astronomy Now and Spaceflight Now. For Daniel, we heard in the briefing earlier that the instruments are linked in some way so they can react if one instrument spots something. How does that work? Is that like some kind of artificial intelligence that rewrites your science program on the fly?
That is. Thank you for that question. This is excellent because this is something I should have explained more detail earlier on. We have an onboard communication system, which uses the onboard wiring. It's called a space wire system for the instruments to talk to each other. So there's some sort of broadcast service, almost like a radio, and each instrument can send information on that broadcast, and each other instrument can opt to listen and then react to it. So the primary mode will be the X-ray imager will detect a flare, and because that's the fastest information propagation from the sun to us with the speed of light. And then the X-ray instrument will say, look, I saw a flare, and flag that to everyone else. So once a second, then the system will say, look, there was a flare, do you want to do something about it? And then the other instruments could go into a burst mode and acquire data at the highest possible cadence for extended periods of time. So a little bit like sports photography. And then when that period is over, they would just go back to normal mode.
Great, back to Marcia at the front of the room, please.
For Guenther, you mentioned actually being able to capture the sounds of the sun. Tell me about that, and has any other solar observatory ever done anything like that?
Yes, this is what is called helioseismology, and it is actually a strongly developing field. Also, astroseismology is now becoming very important. The sun is a big ball of fire, and it has modes that it is oscillating. And if you are looking at the light of the sun, then you can see those oscillations. And we do this regularly now with other stars. We can measure, for instance, their composition inside, their age, and things like that. With the sun, you can, in principle, do that in integral sunlight. You see those modes. But when you then look in great detail, you can see these oscillations locally. And that is what this sound instrument is doing.
And it was first done with SOHO, and then SDO has a dedicated instrument to do it, or Solar Dynamics Observatory, SDO.
So you'll be able to download this and we can all listen in. Is that theoretically what will be?
The hum. Yes.
The hum of the sun.
Yes.
Okay, great, thanks.
Fantastic. We do have some social media questions over here we'll be taking.
Kenny Graddick on Twitter wants to know, how long will it take Solar Orbiter to get to the sun?
So we'll have a cruise phase of just under 2 years to get to our full operational orbit, where we get all the way into the Sun-Mercury distance. However, already in June this year, so just 4 months after launch, we'll approach the sun to half the distance between us here on Earth and the sun. So that'll be the first time when we'll actually get really new and exciting data.
Dirk Wagner on Twitter wants to know, will Solar Orbiter orbit the sun essentially forever after the end of the mission, or will it crash into the sun at some point in the future?
That is an excellent question. We have not decided yet. There are different ways we could take it. We could, again, if there are engineers in the room, you might disagree, but we could try, for example, to get unprecedented data from the atmosphere of Venus. So our instruments were not designed to go into Venus, but that would be a safe way, also in terms of planetary protection, to crash the spacecraft into Venus. That's just one option. You could also leave it in its final orbit. Maybe you could try to bring it a little closer to the sun, beyond the technical capabilities that we know we will survive, just to see what happens, get even better images. Or we could just try to use the last push to get it even slightly higher out of the ecliptic plane. So these are all options, and I think depending on the data we'll get in the next 10 years, we might decide one way or the other.
I mean, just to follow up on that, the phase where we are tilting the orbit so that we can actually reach the poles will only happen after the initial phase. So it is we will observe for 5 years, and then for 3 or 4 more years we will go higher and higher and higher, and that is in principle then only dependent on the performance of the instrument and also of the funding for the operations. But if we do great work, I'm convinced we will. I mean, SOHO is working since 25 years, so no need to shortcut that.
And one more, Matt from Periscope wants to know, how do the sun and solar storms influence us here on Earth?
So we live in the atmosphere of the sun. The solar wind continually moves away, bathes all the planets, and so we are deep in that atmosphere. So every time something happens on the sun, we feel the impact here at Earth, assuming that it's facing us. So you say when the sun sneezes, the Earth catches a cold, and so we feel the effects of the sun. It affects our technology. It can cause problems for GPS spacecraft, any spacecraft in orbit. If they're in or around the Van Allen belts, the Van Allen radiation belts can suddenly kind of engulf a spacecraft that isn't designed to be in there. We see issues with power grids, with pipelines. We obviously see beautiful aurora too, which is my favorite bit. And obviously for us at NASA, protecting our astronauts as part of the Artemis program is of high importance to us, making sure that we totally understand the environment that they will be living and working in. So all your technology is really impacted by everything coming from the sun.
Let me just add to that. A few years ago, there was an analysis of what is the least known element of space weather forecasting. And it basically said, without any uncertainty, that it's the near solar environment where the sources of space weather where we know the least about to make predictions. And so for us, going with Parker and with Solar Orbiter to explore that space really addresses that in a fashion that is unprecedented. The goal is not only to have that understanding, but to put that understanding into models. And especially as we go with astronauts outside of the Earth magnetosphere to the moon and then to Mars, we need to be able to predict far away from the Earth. That's precisely where these models will have the most power and will actually help in a direct fashion these astronauts that we're thinking about right now.
Great. I believe we have some more questions in the room.
Kirby Kaler, Sky News Canada. There have been significant delays in this project. I think the contract was signed back in 2012. Have there been any improvements or upgrades to the instruments while waiting for launch?
I can try to start, and then I will hand over to to Daniel. So I think the problems are when you are developing completely new technology, which we had to do for Solar Orbiter. We also had to do it for Bepi-Colombo. You think about the solar panels, for instance, when you're facing the sun, they are getting so hot that they wouldn't work anymore. So we had to put them on a grazing angle, this intricate heat shield and all of that. So the whole suite of instruments is really at the top-notch forefront of technology. And you do these for the first time, these things, and you can predict how long it will take, but in the end, it takes as long as it takes. And the problem, you don't want to compromise on quality. So we really don't want to give up on the excellence of science. And therefore, we had to accept a delay. But I think since about 2 years or so, we have been straight on our program. So this is life in space, and we try to improve on that, but I think we are doing things for the first time, and you never know what happens.
Yeah. No, I think that's exactly right. And I mean, ultimately, space is hard. And we see that every time again new countries get involved and build their first space missions, it's much easier to build something ground-based and then try it out and fix it iteratively. But here we essentially have this one chance. We just need to get it right the first time, and this is why we build, we prototype, and we test. And we need to iterate it until we are really convinced it will work. And so yes, I mean, ideally you get it right the first time, but often you find out more about the problem while you're trying to solve it, and then ultimately that gives you the better solution. But yes, it does take often a bit longer.
The carbon fiber heat shield was one thing I think that was updated. Is that correct?
Absolutely, that's exactly correct. So the heat shield that we have is a completely new design. We could not reuse the one from Bepi Colombo because it's a completely different mission that flies to Mercury and gets heat both from the sun and from planet Mercury, the reflected sunlight. It also couldn't be one like Parker Solar Probe had because we needed to be able to look through it and have these peepholes. And it's a two-level design where we have a bottom layer that is an aluminum honeycomb covered in carbon fiber skins, and those were difficult because they still had to withstand temperatures of about 300 degrees centigrade. And then there's a gap, and above that gap there's a almost floppy layer of 20 thin shields of titanium with a particular coating that we call solar black, which is completely new for space. So I mean, there have been applications on Earth derived from space materials, and this one was actually the other way around. The people had developed a coating for titanium implants for humans, and they realized that the titanium would bond better to human bones if it had a coating made out of roughly the same material, calcium phosphate. And then they found out that this material was unique. It was absolutely resistant to everything. So you can make it black and it can never get any blacker. It will also not degrade over time or evaporate. So we thought this is our material. But of course, it hadn't been qualified for space, so that took extra time to really get that qualification. It's a small company, a real startup, and we are proud, and they are proud that they've now made it all the way to space.
And you were asking whether the instruments were using this extra time to get improvements. I think it was, in a sense, a two-way street, because the instruments also went to new technologies, and some of them took longer than they originally thought. But I think the good thing is really we have everything up there on the rocket now at the quality that was anticipated before, and even better. For instance, one of the big issues in this sensitive environment is the contamination. You don't want to have dirt in your spacecraft or in your environment, and so contamination control was a huge effort. And now we know that the contamination that we have on the spacecraft is actually more than 10 times better than it was specified. So we have a little bit overdone it, but it is the cleanest spacecraft that has ever been launched.
Back to Steve Young in the middle over here.
Stephen Young with Astronomy Now and Spaceflight Now for Nicky. You've said what a great time it is to be in heliophysics, but with the current fleet and with Solar Orbiter coming in, what gaps remain in your ability to study the sun? And if you won the NASA budget, how would you fill those gaps?
Wow. So I would like a fleet of spacecraft all the way around the sun, both around the equator and over the poles, continually looking down. If I won the NASA budget, that's what I'd like to do. But, you know, I think to Thomas's point, really getting in and understanding the inner heliosphere, we're starting to answer questions with Parker Solar Probe. Solar Orbiter is going to start answering questions immediately. They're also going to start asking questions. There's going to be the unknown unknowns. There's going to be the things that you need to design those next missions for. And so, really understanding this inner heliosphere, understanding the poles is really important. And so, there are many concepts out there as we move into our next decade. There are many scientists who would like to do, a dedicated kind of pole sitter, going over the poles and sort of sitting there for a long time, is a very, very hot, excuse the pun, very hot region of science. Also leaving the heliosphere with a dedicated mission to really go out and study that boundary that protects us from interstellar space. But from my own personal thing, supporting our Artemis mission, making sure we're making the measurements that are so key to be able to protect our astronauts, particularly as they leave the protective bubble of the Earth's magnetosphere, is really key for us. And so we're excited to be supporting that program, and already starting to look at putting instruments on the very first launch of Gateway. So lots of exciting things, but yeah, a nice string of pearls all the way around the sun, that'd be really nice.
Do you mind if I add that kind of from an experiential level? And it's really a profound question because, of course, the honest answer is you don't know because we haven't done this research yet, right? So here's, when we did Soho, and, I was a grad student then, and I went to these meetings, this local helioseismology that you talked about, listening to the sounds of the sun and learning about the structure there, gave a few results that are really important, right? How exactly the structure is, how the material turns over. You saw the movie at the really small time spatial scale, but there's also a larger spatial scale that's really important. One of the results also was there were flows towards the pole. And it turned out the flows were actually at the same kind of temporal scale as the solar activity cycle, which is why Daniel said what it is. Now, so you take all the models that exist as a result of those data, and where are they different? It's how they deal with the polar regions. Well, does it go submerge? Is it like creating a mess there, kind of turbulent eddies? How does it work up there? The answer is that's the real question we need to address, which is, guess why? Solar orbiter goes out of the polar regions. We also, from Ulysses in parallel, we saw that the solar wind up there is so fundamentally different because of some of the measurements that were pioneered there, measurements that are approved upon 10x with the measurements that solar orbiters are doing. So for me, like the question now is really a question that, frankly, when we started with Soho, we didn't know how to ask. But it's a question we now know relates to all of stellar activity. It's not just our own star, it's how that works. That's why we're looking with interest at other magnetic bodies like Jupiter and Saturn, right? Because we recognize, wow, that's similar science. By the way, the Earth magnetic field is also changing, right? The pole is moving down, and the magnetic field is a lot weaker than when I was looking up in some book what the magnetic field is, right? Kind of the Earth magnetic field is also changing. Why? That's the kind of question we're trying to address. And so for me, what's the question we're going to want to know? Of course, the Artemis thing is something very deep to, very motivating to us because of the immediate motivation. We want that in a few years, right? We want to be really in a better shape. But the fundamental question afterwards is really the one that we're after now, right? We don't know yet. Fair?
Maybe I can add something which is true for all of science. You know that our knowledge increases exponentially. But with every new discovery, we open a door and we see 10 more closed doors that we don't understand. So our ignorance grows faster than our knowledge. And so we will not go out of job soon.
Yeah, no, I guess I'll just throw in one of the reasons I continually say it's a great time to be a heliophysicist is there are so many great new missions. There are great new missions being proposed. We have several more in the queue already, launching in the next few years for Helio, and the link to Astro. So, nobody yet asked me why I'm so excited about this particular branch of science, but it is because it is so profound. It has so many impacts. Planets in our solar system, but the ability to go and study a star up close. I mean, it's going to be a while till we can study another star up close. I said a while, not infinite. It will be soon. But to actually, oh my God, we're studying the star. We're right up close to a star. It's amazing. And so you can just say so many more things about other stars, other stellar systems. We know they have stellar storms. And as Thomas said, as we look for exoplanets and other places that would be habitable zones, other Goldilocks regions, studying our star is the way to do it. So it's a great time to be a heliophysicist.
Great. We will go to Simon here in the back.
Hi, Simon Witchcombe, Sky at Night, BBC. I imagine that you'll have a deep sense of relief when you see it safely on its way on Sunday. But how are you going to cope with the tension over the next 2 years before you start getting data back from the spacecraft?
Okay, so luckily we'll have a soft start after the rocky launch that will be really test the ability of the spacecraft to its limits. Once we are in space, it's smooth. We'll commission the instruments, meaning checking out all the subsystems, making sure everything works, and the spacecraft, of course. But then, hopefully by June, the sense of touch instruments, the particle sensors and the field sensors will already be operating. So for them, science is starting already in June, which is fantastic. And then we'll have the first perihelion already mid-June. And interestingly enough, also Parker Solar Probe has a perihelion almost at the same time.
Yeah.
So we are already doing science within the first year. And that will surely keep us busy until November 2021, when we'll then kickstart the full mission with all instruments on.
And I'll say that you never relax, actually. I can tell you Parker Solar Probe just came out of her 4th perihelion, and that I breathed a sigh of relief. I'm getting ready for the 5th one, when I will go back into the panic mode.
And maybe just to add, we have launched Bepi Colombo, as you know, about 1.5 years ago. This will be on its way for 7 years, and it is a stack of 3 spacecraft. So, and the cameras will not see anything before the stack is actually unmounted. Still, we try to do science as much as possible. I mean, for instance, the flybys, when we fly by Venus, when we fly by Earth, we'll get a lot of additional excitement, and so we'll never sleep for 7 years.
All right, we have time for 2 more questions here, please.
Jim Siegel with Spaceflight Insider. The benefits of this mission are pretty profound and very important for on the basis of basic science, and also of travel to other planets. So I understand that. But I'd also like to try to tell my readers, for the average person on the street, in the relatively near term, not 100 years from now, what's in it for them? Is there something that I can tell my readers that they will benefit from in their lifetimes, or even next year or 10 years from now?
Yes, I think they will. I mean, in particular, the effects that the sun has on our infrastructure are humongous. There have been events in the past where our technology was not yet so developed, but there was already huge effects. So, for instance, there was one event where the Carrington event, where the telegraph stations, the paper started to burn in the telegraph stations because the sun has influenced the power lines. There was an event last century when the north of Canada, the whole north of Canada was completely blocked out. The power stations were kind of like dominoes falling out because the sun was affecting the grid. I think we have not seen the biggest solar events yet. I think in the past there were bigger ones. And if something like that happens in the near future, it could really have a profound effect on all the Galileo satellites, the GPS satellites, all of the infrastructure in space. So it is a real direct, even financial impact that this kind of study has.
And I think you made a really good point there, that we didn't have the technology, so we didn't know the impacts. We've also seen now big events. One went off a few years ago off the side of the sun. We didn't know to look for that before. We didn't have the instruments to be able to look for that before. But when we modeled the impact, it actually hit one of our stereo spacecraft, and we were able to take the data. And when it was modeled, it was said that it would have been a larger storm than even the Carrington event. And that was, I think, 2013. I think. But, you know, I talk at schools a lot. I have young kids, and I always like to say, you know, Carrington event and the telegraph system in the U.S. went down for 4 days, and the kids kind of just look at me like, so what? And then I say, now imagine you didn't have your iPad for 4 days. Panic ensues in the classroom. And so, you know, nobody really cared that much because it was a little inconvenient. Now it would be, you know, it would change, you know, life and society as we've come to rely on it. So it's a very different thing.
So would Solar Probe kind of help predict when these things might happen, or is it simply a way of explaining when they do happen, here's why?
It's the improvement of the models that will be so key. And so, yes, right now, if something really big happened and Parker was in there, we would be able to give you the data afterwards and kind of unlock it. But it's really by understanding the physical processes that are going on in the close in the inner heliosphere, and then you know, the poles that Solar Orbiter is now going to add to us, being able to really add the physics to the models. So, we know things happen, but we're not quite sure why. We've seen some smoking guns in the Parker data already with the switchbacks that we published in December, things that, are causing the magnetic fields to coil and then release, which will actually add energy and let it come, be released again. And so, we know that there are big physical processes that are happening in the sun. Once we really know what those are, and again, the importance of the magnetic field at the poles, the processes that are happening that are actually heating the corona and accelerating the solar wind, you can add that physics to these big models that Thomas was talking about. And so that's when you get these transformational improvements in our ability to predict from what we see a number of days before, predicting accurately what is going to impact our planet. Then you can safe a power grid. It's a lot, if you can take down a power grid, it's inconvenient, but then you start it back up again in an orderly fashion. Is very different to a power grid failing.
We
So
are
just
unfortunately
yes.
going to have to wrap up.
Yes. No
But
problem.
I know there were some other questions in the room, and I know there are more answers we want to give. People will be in the room. We can answer more questions after we wrap up. But for those of us on television, we are saying goodbye for now. You may watch the launch starting at about 10:30 p.m. East Coast time on Sunday, February 9th is when launch coverage starts. You can see that at nasa.gov/live. And also for mission updates, you can go to nasa.gov/solarorbiter. We hope you are as excited about this mission as we are. Let's do it.
Go Atlas, go Centaur, go Solar Orbiter.
Thank you.